lecture I am going to introduce you to modal analysis. So why modal analysis is performed? So modal analysis is performed to find out the fundamental frequencies and their associated behaviors, which are nothing but mode shapes. We are going to learn more about modes and mode shapes in the further slides. So modal analysis is a fundamental analysis that is always performed alongside with the static structural analysis to understand the behavior of a product under consideration. So we are going to see an example why modal analysis is important. So here if you take this particular example where there is a centrifugal pump with a motor that has been attached to the frame. For example, let us say this particular motor is running at 3600 rpm. So if we want to find out the frequency, let us say this 3600 revolutions divided by 60, you are going to get 60 Hertz frequency. So what happens, this particular motor is working at a frequency of 60 Hertz. Then if the combined frequency of the total motor, pump as well as the frame is equivalent to 60 Hertz or somewhere nearer to 60 Hertz, what happens, this working frequency of the motor is going to coincide with the natural frequency of the total system. Then what happens, a phenomenon known as resonance will occur, and this is going to destroy the total system. So resonance is nothing but vibration of a body with very huge amplitude, which eventually creates a failure or leads to failure. That is why structures cannot be declared safe only with the load withstanding capability, but it should be safe considering the structural dynamic aspects as well. Then one of the best example was the Tacoma's Narrows Bridge, which was built in 1940s in the US state of Washington. The failure of the bridge occurred from a never seen before twisting mode due to the air. So what happens is from the winds that were blowing at 40 miles per hour, a torsional vibration mode has been established, and that has led to the failure of this Tacoma's Narrows Bridge. Before that, if we had studied all the different modes and tried to change the frequencies or natural frequency of vibration of the body, then this disaster wouldn't have happened. Then so coming to the major terms that we should know before conducting frequency modal analysis, the first term is frequency. So frequency is nothing but 1 by time. So for example, let us say if milk delivery boy is visiting our house every morning at a fixed time, so his frequency is 1 per day. Likewise, if a patient has been prescribed by the doctor that he has to take medicines for 3 times a day, then the frequency is 3 per day. So for now what we are going to do is we are going to take a steel ruler example, and we are going to place one end on the table, and then we are going to just vibrate this end. So what happens, so if you see, this is the mean position of the ruler when it is undisturbed. When I have disturbed it, what happens, it is going to change from this mean position, and it is going to come down, and then it is going to go back. So the time taken for completing one cycle is nothing but time period. So frequency is 1 by time period. Then frequency omega n, natural frequency omega n equal to root of k by m for a circular frequency, and its units are radians per second. So most of the commercial softwares, what happens, the frequency is going to be given in the form of f, where f equal to 1 by 2 pi root of k by m, as 1 by 2 pi root of k by m. So we need to convert rpm to hertz. For example, say engine is running at 6000 rpm, that means we need to divide 6000 by 60 rps, or say it is going to get 100 hertz. So coming to the next important term was what is known as the natural frequency. Natural frequency is nothing but the frequency at which a body vibrates if disturbed and allowed to vibrate without any external force. So without applying an continuously external force, at some frequency the body is going to vibrate. So that particular frequency is known as a natural frequency. See, for example, here we have taken a ruler and we have applied a small disturbance here, then it is going to vibrate for some time like this, and this is the natural frequency without even applying any other external force. Then every system, mechanical system or any system, can be represented in the form of stiffness, which can be represented through spring, and this is a dashpot which represents the damping, and m is the mass of the total system, and this is the unit displacement here, and this is the force. U of t can be taken as the force. Then so what is mass? So mass is nothing but the quantity of matter that is present inside the body, and then coming to the stiffness, the force required to produce a unit deflection. For example, if you take a spring and you want to produce unit deflection, you need to apply some force. Depending on the material and shape of the spring, you need to apply more force in some cases, you need to apply less force in some cases. That is stiffness. So coming to the third property, damping, the property or the characteristic of a body to lose energy or absorb energy. So what happens is, for example, if we go back and then come to the example of this ruler, what happens is once I disturb this ruler, after some time it comes back to its mean position and stops vibrating. So this is the inherent behavior of any object. What happens is, due to the presence of damping, these vibrations are going to be decreased gradually, and after some time what happens, the vibrations become zero. Then damping can be divided into three types: structural damping, which is an inherent property of the material or the structure. Then the viscous damping, this is the damping that is caused due to the fluids. Then the third one is the dry friction or the Coulomb damping. So this is the damping which occurs due to the contact between two or more surfaces. So in our free vibration analysis, we are not going to consider this damping effects, we are only going to consider the mass and stiffness effects. So then coming to the definition of mode and mode shape, the frequency at which the body vibrates is given by the modes, and for natural bodies what happens is there are infinite number of degrees of freedom for a natural body, so obviously there are infinite number of natural frequencies for a body. Then coming to the mode shape, it just represents the shape or the pattern in which the body is going to deform when it is going to vibrate at certain natural frequency. For example, if say some 100 hertz, it is going to vibrate sidewards, but at 200 hertz it is going to vibrate up and down. So with this mode shape, we will be able to predict in which direction it is going to vibrate at that particular modal frequency. So coming to the natural frequency, fundamental frequency, the lowest frequency that is obtained after performing modal analysis is known as the fundamental frequency of that particular object. Then what are the application of these modal analysis? So as we have seen earlier, we can apply this modal analysis in aerospace, automobile, marine, sports, construction, offshore equipment, etc., etc. All the fields where FEA is dynamic analysis is applied, the starting point will be a modal analysis. So all the fields where FEA is applied through dynamic analysis, the starting point is modal analysis. So in the next lecture, we are going to see how we can perform a modal analysis and assumptions taken for modal analysis inside ANSYS Workbench. Thank you. To introduce you to the modal analysis and how modal analysis can be performed inside ANSYS Workbench. So in order to access modal analysis, you need to go to the analysis systems. In the analysis systems, you need to select the modal analysis system and drag it and drop it on the project schematic. As I have told earlier, the options, the steps you need to perform will be from the top towards the bottom. Then so basics of free vibration analysis. So in modal analysis, we are going to conduct free vibration analysis, and the one is the pre-stressed vibration analysis. So the first we are going to learn about basics of free vibration analysis. So what happens here, see, for a linear equation of motion where mu double dot plus ku equal to 0, here usually there will be a force term, but what happens in free vibration analysis, we are not going to apply any types of loads on the body. We are going to constrain the body and then we are going to find out its natural frequencies and mode shapes. That is why this F term is 0 here, and then this K term is nothing but the stiffness matrix, and this is the mass matrix. So this is nothing but the say displacement, and this is the acceleration. So if you take this displacement in its normal form, the harmonic motion equation is psi I sine of omega I t plus theta I, but when we differentiate it for 2 times to get the acceleration, we are going to get this particular value. So we are going to substitute this particular value in this particular equation to change the equation into this form, where k minus omega square into m into psi I equal to 0, because remember this is 0 because this is a free vibration analysis. So as shown in the previous slide, the final equation is k minus omega I square m into psi I equal to 0, where k and m are constant because we are going to perform linear modal analysis, where we assume linear elastic material behavior is present, small deflection theory used, and there are no non-linearities that have been included. Here there should be another term matrix known as the C, which is not present. C is nothing but the damping matrix. What is happening is, in the free vibration analysis we are not going to consider the damping effect also, and as I've told you, we should be having a force matrix which is also not present, because in the free vibration analysis there is no excitation of the structure, or there is no external excitation of the structure. And C, the structure can be constrained and the structure can be unconstrained. Then so coming to the geometries, we can use both solid bodies, surface bodies as well as line bodies in order to perform the modal analysis. In some cases we can use the feature of point mass or distributed mass to add mass without having any additional flexibility that is being added to the modal analysis. Then coming to the material properties, for any for any type of dynamic analysis, the major options or the major material properties you need to define are the Young's modulus, Poisson's ratio and the density, because from the Young's modulus and Poisson's ratio it is able to conduct, or it is able to create the stiffness matrix. But if you want to create the M matrix, which is the mass matrix, then you need to specify the density of that particular material. And coming to loads, there are no structural as well as thermal loads are applied or can be applied in the free vibration analysis. So any type of structural or thermal loads we cannot apply directly in modal analysis. And then if the supports of the body are not given, then the body moves in a rigid body fashion. So what happens if the body is in a rigid body mode? The frequencies, the first 6 natural frequencies of the body will be 0 or nearly equal to 0. And remember, the choice of the boundary conditions will affect the mode shapes. Depending on how we constrain the geometry, the mode shapes of this particular, the frequencies and the mode shapes of that particular object is going to change. Then we can use different types of contacts here in modal analysis also. Then in the solution settings, we can find out, we can set the software to find out the number of modes we want. Like for example, if I say I want to find a 12 modes, I can just give an option here in the analysis setting, or otherwise if I want to find out the frequency between some range, like for example here you see I want to find out the frequencies of the object between 100 Hz to 500 Hz range, so I can also give it like this. In addition to all of these things, I can also ask the software to calculate the stresses and strains and reactions that are occurring due to this particular type of vibration, this particular vibration at the natural frequencies. Then coming to the results, based upon no excitation or there is no other external force that is being applied, we are going to get the mode shapes as well as the natural frequencies. Then coming to the next type of modal analysis, which is the pre-stressed modal analysis or vibration analysis. So what happens in the previous case, we haven't had any type of forces that are applied, but what happens, see, if in the case of guitar string, we want to analyze the natural frequency of this particular string. So what happens, this string is attached to this guitar at some tension, with some tension. So in order to simulate such type of cases, we need to be performing this pre-stressed vibration analysis. Here also, for example, this particular say what is the cables that are used for attaching this deck to this pillars, they are also under some pre-stress. So what happens, while in if the pre-stress that is applied is in tension, it will cause the frequencies to increase, and if it is the compressive state of stress is there, then you can say that it decreases the natural frequencies. So what happens is, in order to access this type of pre-stressed modal analysis, first you need to perform a simple static analysis, and from that simple static analysis you need to say bring this solution as an input to this modal analysis. Don't worry, we are going to see this example as well in the coming lectures. Then, so coming to the equations, so what happens, the basic equation, as I've told you before, Ku equal to F, or say Kx equal to F, where this is the stiffness, this is the force matrix, this is the say displacement matrix. What happens is, from this performing static structural analysis, we are going to get a stress stiffness matrix. So once we obtain the stress stiffness matrix, we are going to add this stress stiffness matrix, which is denoted by S, to this already existing stiffness matrix of K. So the equation becomes K plus S minus omega I square m into psi I equal to 0. So what happens, the free vibration equation has been modified to include the S term, which is nothing but the stress stiffness analysis, which comes from structural analysis. So with this we have completed this theory regarding the free vibration analysis as well as the pre-stressed vibration analysis. So in the next lecture we are going to see how we can perform different types of modal analysis, and what are the results we are going to get, and how to interpret those results in the coming lectures. Thank you.